Hello, good morning everybody. I am Seshagiri Rao, Associate Professor in the Department of Electronics and Communication Engineering. Today I am going to discuss about the internal architecture and pin configuration of 8051 microcontroller. So the microcontroller, it is a computer implemented on a single chip. So microcontroller means it not only contains the CPU but also internal memory and some other peripherals like ADCs and DACs. And 8051, it is the first microcontroller of MCS51 family, and this is manufactured by Intel Corporation. And this was released into the market in the end of 1980s. So the 8051 family, it has many enhanced members and enjoys large market share, and it is about 40% among the various microcontroller architectures. So the salient features of 8051 microcontroller are, it is 8-bit CPU. So that means the registers inside the microcontroller 8051 are of 8-bit capacity, and it has on-chip clock oscillator. Only you have to connect the crystal outside, and it has 4 kilobytes of on-chip program memory and 256 bytes of on-chip data memory. And other important features are, it has 64 kilobytes of program memory address space. That means the internal program memory is 4 kilobytes. In case required, you can interface 64 kilobytes of external program memory. And also you can interface 64 kilobytes of data memory also. And it has 32 bidirectional I/O lines in the form of 4 8-bit ports, and these can be individually addressable I/O lines also. You can individually address these 32 I/O lines also. And it has 2 16-bit timers or counters, namely T0 and T1. So this T0 and T1, there are 16-bit timers, and it has a 16-bit address bus multiplexed with port 0 and port 2, and 8-bit data bus multiplexed with port 0. And it has a full duplex asynchronous receiver transmitter. So you can use this 8051 for serial communication also. And it has 5 vector interrupt structures with 2 priority levels. So there are 5 interrupts, and 2 are external interrupts and 3 are internal interrupts. So this is a block diagram of 8051 microcontroller. So it has a CPU, and it has 256 bytes of RAM and 4 kilobytes of ROM. So this ROM can be used for program purposes, and RAM can be used to store the data. And as I have mentioned just now, there are 2 timers, timer 1 and timer 0. So this timer 1 and timer 0, these are 16-bit timers. So that means they start counting from 0000H to FFFFH. So, and once the maximum count is reached, the counter again rolls back to 0, and again it starts counting from 000H. And these are the 4 I/O ports which I have discussed just now: P0, P1, P2, P3. These are 8-bit I/O ports. So total 32 pins are allocated for these 4 ports. And the serial port which can be used for serial communication. TXD is transmit data, and RXD is receive data. So these are the pins that can be used for serial communication. And we have uh, built-in oscillator circuit. Only you have to connect the crystal outside. And this is the interrupt control, and there are two external interrupts and three internal interrupts. So this is a block diagram of 8051 microcontroller. Next, so let us discuss about the architecture of 8051 in more detail. So the processor includes the arithmetic and logic unit, instruction decoder, timing generation unit, and A and B registers and status register are part of the CPU. So A stands for the accumulator, and B register and the status register. And arithmetic and logic unit, it performs for the computing functions. So the accumulator is 8-bit register, and for arithmetic and logic operations, one of the operand is kept in the A register, that is accumulator. And after arithmetic and logic operations, the result is stored in A, and depending upon the type of result, various flags are affected. So the flag register, it contains the carry flag, the auxiliary carry flag, overflow flag, and the parity flag. So if the arithmetic computation results in overflow of carry or in addition or borrow of carry during subtraction, then carry flag is set. And what is auxiliary carry flag? When there is flow of carry from the lower nibble to the higher nibble during addition operation, or when there is a borrow of carry from higher nibble to the lower nibble during subtraction operation, the auxiliary carry flag is set. And overflow flag, if the result is out of range, then overflow flag is set. If there are even number of ones in the result, then the parity flag is set. So the flag register in case of 8051, it is 8-bit register. Now let us see the instruction decoder and control. So the instruction decoder and control, these are part of timing and control block. So when the instruction is fetched from memory and it is loaded to the instruction register, and then the decoder, it decodes instruction, and then it formulates the sequence of events that are to be followed. So the instruction register, it is not a programmable register, and it cannot be accessed by the programmer or the user. Only it is used to store the instructions that are fetched from the memory. And the timing generation and the control unit, it synchronizes all the microcontroller operations with the clock. So the clock, the machine cycle in the case of 8051 controller contains 12 clock pulses. Whereas if you see the 8086 microprocessor, each machine cycle consists of 4 clock pulses. In the case of 8051 microcontroller, each machine cycle consists of 12 clock pulses. So this is the detailed block diagram of the 8051 microcontroller. This is the port 0, and which has 8 pins, and port 2 which has 8 pins, and these 8 pins are designated as P2.0 to P2.7. And port 0 8 pins are designated as P0.0 to P0.7. So P0.0 to P0.7. So these are the 8 pins. Okay. And RAM, just now we discussed that there is a 256 bytes of RAM. Out of that, 128 bytes are actual RAM, and another 128 bytes are allocated for the SFRs. SFR is nothing but the special function register. Then this is the port 0 latch, and this is port 2 latch, and this is the ROM. ROM is 4 kilobytes of ROM is there for 8051 microcontroller. If you go for 8052 microcontroller, you have 8 kilobytes of ROM. And this is the arithmetic and logic unit. So one of the operand is the store. One of the operand comes from the accumulator, and another operand is taken from the B register. And accumulator, it process, or it does the arithmetic logic operations, and depending upon the result, the PSW is affected. What is PSW? PSW is nothing but the program status word register. Program status word register. Okay, and this is the timing and control unit, and this oscillator, and to that external crystal is connected, and this is a port 1, and these are the 8 pins which are meant for the port 1, and this is port 3, and these are the 8 pins which are meant for the port 3. So this is the functional block diagram of 8051 microcontroller. Now let us discuss about the registers in more detail. So the A register, the address of it is E0H. So this is similar to any Intel microprocessor. So this 8051, it has A register, and A register is 8-bit register, and this A register is used for all arithmetic and logic operations, and it has direct connection with the ALU. So one of the operands or the data is stored in the accumulator, and after operation is performed, the result is stored in A. And suppose if you are performing the multiplication operation, one of the 8-bit operands is stored in B register, and after the operation, it stores the lower byte in A register. Okay, and in division operation, it holds the 8-bit dividend, and after operation, the quotient is stored in the accumulator. So this is also used in indexed addressing mode to take the information from the program memory. And A is the bit addressable register. You can address the individual bits of A. You can address the individual 8 bits of the accumulator. And what is B register? B register, it is used for during multiply and divide operation. In multiplication, one of the 8-bit operands is stored in B register, and after division, it stores the higher byte result in B register. So it is like this. One of the operand is there in A register, and another operand is there in B register, and after the multiplication operation, the higher byte goes to the B register and the lower byte goes to A register. So this is how it takes place during the multiplication operation. And in case of division operation, the B register, it holds the divisor, and A register holds the dividend, right? So A by B. So B, it holds the divisor, and after the operation, the remainder is stored in the B register. So R goes to B, and the quotient goes to A. So A and B are the very important registers. So in division operation, the B register, it holds the divisor, and after the operation, the remainder is stored in the B register. Okay. And coming to the PSW register, the address of it is D0H, and it is 8-bit register, and it contains it has direct connection with the ALU, and depending upon the result of operation, the individual flags of program status registers are activated. So this is the format of the program status word register. So you have here CY. CY means the carry flag. AC means the carry auxiliary carry flag. F0 is not used. RS1, RS0. These are the RS1, RS0. These are the bits that are used for selecting the register banks. And OV is the overflow flag, and P is the parity flag. RS1, RS0 are the register bank selection bits. So if it is 00, bank 0 is selected. If it is 01, bank 1 is selected. If it is 10, bank 2 is selected. If it is 11, bank 3 is selected. And F0 is not used. AC is the auxiliary carry flag. And CY is the carry flag. So these are the descriptions of individual fields of the program status word register. Now let us see the case of memory. Memory, you have internal memory and you can interface external memory also to 805 microcontroller in case it is required. So the memory of 805 microcontroller, it is of two types: volatile memory and non-volatile memory. And the internal volatile memory is of 256 bytes, and out of that 128 bytes are the internal RAM, and another 128 bytes are for SFRs. SFR is the special function register. So this in this internal RAM, you have 80 bytes are allocated for general purpose RAM. And uh, and 32 bytes are allocated for the register banks, and there is a bit addressable RAM which is of 16 bytes. So 128 bytes internal RAM is organized this way: 80 bytes of general purpose RAM and 32 bytes are allocated for register banks. Bank 0, Bank 1, Bank 2, Bank 3. Each bank contains 8 bytes. So 8 into 4, 32 bytes are kept aside for the register banks. So remaining is 16 bytes, which are nothing but the bit addressable RAM. So the system stack normally it uses the general purpose RAM, which is 80 bytes, and only little space is left for general storage. And the general purpose RAM, it can be accessed during the using direct or indirect addressing modes. And SFRs we have the address range 80H to FFH, and not all locations in this range are used. Only few are used. Around 23 SFRs only are used, and any attempt to address the undefined locations, undefined SFRs will cause unpredictable errors. So each SFR it has a very specific function. So these SFRs they have the address in the range 80H to FFH, and it reflects the name of it reflects the purpose of SFR. So though there are 128 bytes of SFR, only 21 SFRs are used in the 805 microcontroller. And undefined SFRs should not be accessed, just as I mentioned you, because it may lead to unpredictable results in unpredictable errors. So CPU and internal peripheral modules they use the SFRs for performing the desired operation of the microcontroller. The SFRs they contain input-output ports, control registers, timers, and serial ports, etc. So just now, as I mentioned you, the 128 bytes for register banks we have 32 bytes. So they lie in the address range 00 to 1FH, and the bit addressable RAM which is 16 bytes. It occupies the address locations in the range 20H to 2FH, and general purpose registers they occupy the address in the range 30H to 7FH, and special function registers 80H to FFH. Now let us discuss about the IO port and the peripherals. So 8051 microcontroller, it has 4 8-bit parallel ports, port 0, port 1, port 2 and port 3. So these ports, they can be used to send or receive the data, and each port can be configured as input or output port. So port 0, it is used for the low order address and the data pins. See, in case it is required, we can interface the external memory to 8051 microcontroller. So for that, you need 16 address lines. So the lower byte of address is provided by the port 0. Port 0 takes care of the lower byte of the address, and the lower byte of the address is AD0 to AD7. And which port provides the higher byte of the address? Port 2 is used for providing the higher byte of the address, that is A8 to A15. So these AD0 to AD7, they are multiplexed lines. They are used for address as well as for the data. And port 3 is used with the timers, serial port, external interrupt, and for sending control signals to external data memory. So port 3, it contains 8051 microcontroller, it contains timers, timer 0 and timer 1, and these both are 16-bit timers, and they work in the timer mode or the counter mode. In timer mode, the clock pulse comes from the internal clock, whereas in counter mode, the clock pulse comes from the external source. So this supports the serial data transmission using universal asynchronous receiver transmitter. And the bit addressable RAM, just now I mentioned to you that it is 16 bytes. Because it is bit addressable RAM and this is a bit address in the range, this is a byte address and the corresponding bit address. So for 20 byte address, the bit address is 00207. Then for 21, 21 it is 082 0F. For 22 it is 10217. And finally for 2F, it is from 782 to 7F. So there is a this is a bit address and this is the byte address. So total is 16 bytes. This is the detail of the bit address internal RAM, which is 16 bytes. And for special function registers, 128 bytes are allocated, but only there are 21 SFRs. And the name itself indicates the purpose of SFRs. For example, accumulator, the address is E0H, and B register, the address is F0H, and stack pointer it is 81H. And similarly for interrupt priority control register it is B8H, and interrupt enable controller A8H, and timer and counter higher byte 8CH, and power control 87H, and serial control 98H. Like that, the name indicates the purpose of SFR. So only 21 SFRs are used out of 128 bytes. That means only 21 bytes are used out of 128 bytes, and unallocated SFRs should not be addressed, should not be used, because it is going to result in unpredictable errors. So this is a pin diagram of 8051 microcontroller. It is a 40 pin IC and available in DAP, dual line package. So out of that 40 pins, there are 4 IO ports, 4 8-bit IO ports. So 4 into 8, so 32 pins have gone there. Then we have the VCC 1 pin, then ground 1 pin. Then after that we have for crystals, we have 2 pins, crystal 1, crystal 2, there are 2 pins. Then after that we have EA pin, EA bar we have 1 pin, then ALE, 1 pin, then PSEN, the program's status enable, that is 1 pin. So there are total 40 pins. And it works with a single power supply, which is 5 volts. And you see here, this is the circuit for the reset and connecting the external crystal. And here it shows the 12 MHz crystal, and this is a circuit for the power on reset. See, initially when power is switched on, the voltage across the capacitor is 0. So all 5 volts appears between this RST and VSS. Slowly what happens? The capacitor gets charged. So when the capacitor gets charged, the voltage across the RST and VSS, it becomes 0. So a pulse is applied like this, and the 805 microcontroller gets reset. And this is the circuit for power on reset. For manual reset, what is done? A switch is provided here. So whenever you want to reset the microcontroller manually, a push button is provided across the capacitor. When push button is pressed, then what happens? The voltage across the capacitor becomes 0, and a high voltage is applied momentarily at the reset pin, and the microcontroller gets reset. And when the microcontroller is reset, the internal registers are initialized to the default values. Mostly they are all initialized to zeros. So these are the various values of the registers when the reset is pressed. See, all are initialized to 00, but stack pointer is initialized to 07H, and the ports are initialized to FFH. And the IP is that is the interrupt priority register. It is initialized to 00, and IE is the interrupt enable register, that is also initialized to 00. And the PCON register, of course, is initialized to unknown values. So mostly all the registers are initialized to 00 when the reset is pressed. But the stack pointer is initialized with 07H, and the ports, 8-bit ports P0, P1, P2, P3, they are initialized to FF, and interrupt priority register and interrupt enable register, they are initialized to 00H. The timers, of course, they are initialized to all zeros when the reset is pressed. Now, the port 3, it has some alternate functions, and port 3.0, that is pin number 10, it is used for RxD to receive the data in serial communication, and port 3.1, it is used to transmit the data during serial communication, and P3.2 and 3.3, they are used for interfacing the devices, and those devices can request the service of the microcontroller when it is needed. So these are meant for the external interrupts, pin 12 and pin 13. That is port 3.2 and port 3.3. And pin 14 and pin 15, they are the external inputs. You can provide external counter input to pin 14, and for timer 0 and for timer 1, you can give the external clock pulse at pin number 15. And pin number 16 and 17, 16 is the external data memory write, and pin number 17 is the external data memory read. So these are the alternate functions of port 3. Now, as far as the external ROM is concerned, if your application is simple, you can use the internal data memory and program memory. But for big applications, in case it is required, you can interface the external RAM or ROM. So when you are interfacing external memory, the EA bar pin has to be connected to ground. So when EA bar is connected to ground, the 8051 fetches instructions from the external ROM using PSEN, program stroke enable. So the address of the external ROM is going to be 002 FFFH. So, but if EA bar is connected to ground, connected to VCC, then it fetches instructions from the on-chip ROM, which is 4 kilobytes. So, in that case, the address is in the range 0020 FFFH. And for addresses 10002 FFH, it fetches instructions from the external ROM. So, in that mode, 60 kilobytes of external ROM can be interfaced with 8051 microcontroller. So, if EA bar is connected to VCC, 4 kilobytes of internal ROM is used and 60 kilobytes of external ROM can be connected. But if EA bar is connected to ground, all memory is outside the microcontroller. Total 64 kilobytes are outside the microcontroller. But if EA bar is connected to VCC, 4 kilobytes are within the microcontroller and the remaining 60 kilobytes are outside the microcontroller. So, for outside the microcontroller, to access those 60 kilobytes, we use the address in the range 100H2 FFFH. So, this data can be stored both in internal and 64 kilobytes of external data memory. So, here you see when external memory is used, as I have mentioned, P0 is used to provide the lower byte of the address, and the lower byte of the address is 80 to 87. And when address is available on these lines, the ALE pin goes high, so that is used to latch the address when address is available. And the remaining time, those pins are used for the data. And P2, of course, it provides only the higher byte of the address, that is A8 to A15. So, this is how the data bus and address bus and control signals are used in 8051 microcontroller. And P3.6, 3.7, these are the write bar signal and read bar signal. And when data has to be read from the external memory, then this P3.7 is activated. When data is to be written, then P3 signal is activated. So, you see here, when EA bar is connected to ground, total 64 kilobytes is 000H2 FFFH, and this is external to the microcontroller. So, it is total 64 kilobytes is off chip. But if EA bar is connected to VCC, 4 kilobytes of internal ROM is used in the address range 002 0FFFH. And from 100H to FFH, there is 60 kilobytes is going to be the off-chip ROM. And as far as for data applications, we have the total of 256 bytes. And so this is the 128 bytes SFRs, and this is 128 bytes of the RAM, which is, and out of these 128 bytes, just now I mentioned you that 80 bytes are general purpose RAM, and 32 bytes are the register banks, and 16 bytes are bit addressable RAM. So this is how the off-chip and on-chip, the program memory are planned in 8051 microcontroller. So what is the stack? The stack, it is a last in, first out memory. So you can use stack for all read and write operations, and the information that goes last will come first. So this is called as LIFO, last in, first out. So the stack can be implemented by hardware or software, and hardware stack, it is designed using a set of high-speed registers so that you can have the fast response, but the disadvantage is that the size of the stack is limited. And PIC microcontroller, it contains a hardware stack, and in 8051 controller, the stack is implemented by the software. And the software stack is last in, first out data structure that is implemented by using a number of RAM locations. And general purpose RAM of 805 microcontroller is used for stack purposes. And you see here, for stack we use the push and pop instructions, and after 3 push instructions, after one push instruction, the stack pointer is incremented by 40H, and after 2 operations it is incremented to 4, and after 3 it is incremented to 42H. So in the first operation, 0, 0 is pushed to the stack, then 8, 8, 8 is pushed to the stack, and after third push operation, FF is pushed into the stack, and the stack pointer is updated as 42H. So these are the contents of memory and stack pointer after pop instructions. In pop instruction, the data is taken out from the stack. So the last data which has been entered into the stack, that is the one which is taken first. That is why it is called as last in, first out. So these are the contents of the stack pointer after 2 pop instructions. So these are initial contents of memory. After the pop operation, it becomes the stack pointer, it becomes 51H. After second, it becomes 50H. I have taken most of the information from the 805 microcontroller hardware and software applications by the Tata McGraw-Hill publishers, and authors are Dr. Uday Shankara and Mallikarjun Swamy. I convey my special thanks to them because I have taken some information from their book. So with this, I conclude today's session on the internal architecture and the pin configuration of 8051 microcontroller. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.